It has to be combustion in an open system, though. Yeah, exactly. Then what we would do, instead of like we said back here, where we said like it was CO2 plus water plus energy, instead of saying plus energy, we would then just write delta H is equal to negative 802.5 K kilojoules. I don't know why I didn't give myself enough space for that.
Wait, why do you have that?
So instead of writing CO2 plus 2H2O plus energy, I can write that I write my basic reaction, like we know combustion to be, and then that is my energy. That's how much energy is released, 802.5 kilojoules.
So that was just, how do you know that's that much?
Because if I went and I did the energy of carbon dioxide and the energy of 2 moles of water and added those together, yeah, and then I subtracted the energy of methane, then I should get 802.5.
Okay,
Oxygen won't have a value. Elemental groups don't have values. Nolan.
that you have to the hydrogen in the last part.
2H2O. Yeah, 2 waters. Okay. In exothermic or endothermic, it's positive. So if I look at this one,
Is that all three or all two?
what here? O3. This is iron 3 oxide. So if I had 2 moles of iron 3 oxide and I reacted it with 3 moles of carbon, I should end up with 4 moles of iron and 3 moles of carbon dioxide. And what kind of reaction is this? Single replacement. Okay. But because I had to break bonds, I had to break apart Fe2O3 to come up with Fe and then CO2. My delta H is going to be equal to positive 467.9 kilojoules.
What's after the Fe3? It's Fe3 something.
Here? Here?
Yeah.
Fe solid.
Oh, it's just the
State of the compound? Yeah. It's just been so long since we've done this. Like a year. Okay. The second way that we can show it is we can take those values and put them right into the reaction. So we call that a thermochemical equation. So if it's exothermic, we write the energy value on the product side. And states are very, very important because there is a different value for water as a gas than as water as a liquid. So states are really important. So where we've been lazy in the past, now we gotta step up to the plate, put them back in. Okay, so now what I've done is like here, where I have the word energy, now I actually put that number in, 802.5. Okay. All right. I can't handle junior high right now. Okay. Endothermic reactions, then what we do is we take that energy and we put it on the reactant side, we have to add it in. So notice here, it's a negative 802.5. Whoops, 802.5. But here we're adding it. It's part of the products. It's being released. So it's positive 802.5. Okay? Over here, okay, we add it in on the reactant side. Okay. So, hang on, Harveys. When we see this here, this 802.5 and this 467, what that means is for every 1 mole of methane and 2 moles of oxygen, the reaction will release 802.5 kilojoules of energy. Okay? Of energy. Release 802.5 kilojoules of energy. So for this one here, for every... No, because I'm saying I released it. Yeah, it's okay. I put the words in. So for every 2 moles of iron 3 oxide and 3 moles of carbon, that reaction requires 467.9 kilojoules of energy. Or you could say 467.9 kilojoules is absorbed. But I find it's easier to understand that it requires that kind of energy. Yeah, requires and releases. Okay? Does that make sense so far? This part here is a little bit confusing because if we do it in delta H notation, we have to write the negative if it's being released. But when we do it in thermochemical equation, we put it as like it's plus this. Not that it's positive, but that it's being added. It's a product. I don't know. It makes sense in my brain, but okay. Well, we'll get there.
So every time I go down kilojoules, I wrote kilograms.
That's physics. In chemistry, we work at the milligram gram level. Microgram. Okay. Energy term in thermochemical equation delta H notation is specific for the amount of molecules of reactants or products in the equation. Okay? So if we did this, The enthalpy change is proportional. If we did this, if we said that there was 2 moles of CH4, we doubled everything, let's say. Our delta H would be, because we said back here, for every 1 mole of methane and 2 moles of oxygen, it was 802.5 kilojoules. If I doubled it, it's going to be double the amount of energy. Right? And because this is delta H notation, I need to put the negative there because it's released. Yay or nay? Okay. Now if I did this, if I tripled my iron 3 oxide, oops. Don't write a plus sign there. Or a thing. I want to write a plus sign there. I would have to triple the amount of energy that it would require. So what's 3 times 467.7 kilojoules? How much? And I would get 12 irons and 9 carbon dioxides. So it's proportional. If I double it, the energy doubles. If I triple it, the energy triples. If I half it, the energy is half. Okay? And then the other one that I really enjoy, I say that with a little bit, is diagrams. Let's draw it out. What does exothermic energy look like? What does endothermic energy look like? This is going to be called a reaction coordinate. And this is our potential energy. Excuse me. In kilojoules or joules. Hello. Okay, in an exothermic reaction, energy is released. So do I need a lot of potential energy or a little bit of potential energy?
What are we talking about? Exothermic?
Exothermic. Energy is being released.
So your potential energy would be low.
Right, my potential energy would be low. And my reactants up here, I want these to line up. Okay, and so there's this net difference here. We got lots of things. There's lots of information on this graph, okay? Our reactants are going to have high potential energy. I'm going to take a shortcut and write it like that. High potential energy. And our products are going to have low potential energy. Yep. This piece here, the difference between the two is our delta H value. Pardon me? Okay. You're good? Okay. And then what we can say, though, is that the decreasing value, the decrease in delta H, no, that's what we resulted. Oh, my word. Let's start over. That's what I want to write. Thank you. You guys should come write my notes. I won't have to worry about this. The decrease in potential energy means that energy is released. Okay? So when I say a reaction coordinate here, an example would be, this would be CH4 plus 2 O2s. And then down here, my products would be 2 CO2s and 4 waters. That's what it means by reaction coordinate. You put your reactants on the one bar and your products on the other bar. Now, an endothermic reaction, this is called,
How would you get 2CO2 plus 4H2O if you only have 4 carbons as a reactant, or 4 oxygen?
well, I don't know, because I doubled it. It should only be 2.
And then it
would have been easier to add a 2 out front. So there should be 2 here. Yeah. Good catch, Charlie. Okay. So they call this a step-down reaction. Exothermic reactions are a step-down reaction. Now, what happens in an endothermic reaction? It's the opposite. We have low potential energy because they don't want to break apart. Okay, so the delta H value is an increase. Okay, delta H value is an increase in energy, in potential energy, so therefore energy is absorbed. And that looks like this. Divided by 3. So the reaction coordinate, you just write the reactants under the one side and the products on the other side. Okay, let's look at some questions. Let's look at number 3 and 4 on page 346 and number 2 and 5 on page 350.